What is atom? What is next? It's our program for first lecture. Yeah. Atom structure, what is radioactivity, atomic radiation, and discuss some interaction of radiation with metals. So radioactivity is characterized by transformations of the unstable matter into stable one. Maybe it is possible to switch off this one. So again, radioactivity is characterized by the transformation of unstable nuclei into the stable one. And however, these atoms, this daughter nuclei actually, may be unstable too, and will decay further to different types of decays, different chains of decays, until they reach some stable condition, stable nucleus. So radioactive nuclides, also called radionuclides, can emit ionizing radiation as they decay. The emitted radiation can be corpuscular, it can be particles, or electromagnetic in the form of gamma rays, or both. The lecture discusses the main types of nuclear transformations and radiation. When radiation passes through matter, it interacts with atoms and molecules. This interaction leads to the scattering of radiation energy and causes radiation-induced changes in the substance. Then these changes leads to ionization and excitation of atoms and nucleus. The primary radiation effects of the interaction of atoms and nucleus. The primary radiation effects of the interaction of radiation with biological tissue initiate subsequent biological effects, which can manifest themselves in the form of various diseases, the effects of ionizing radiation. So all the related biology will be discussed in lectures by Professor Udalova, and we will discuss the fundamentals of these processes. Next slide. So all substances that exist in nature are made of atoms. Usually the model of an atom is depicted as a nucleus in the center of the slide, located in the center of the electron cloud, which is represented as a set of electrons shells with electrons rotating in orbits. Of course, if you know quantum mechanics, you understand that this representation is slightly not correct, because we cannot place the electron in particular spot on this orbit. We can discuss only the probability of this. But anyway, it's just for the first representation of this atom. So the atomic nucleus is the simplest structure that determines the chemical and physical characteristics of atoms. According to modern concepts, the nucleus is closely related to nucleons, like protons and neutrons. And protons and neutrons have almost the same masses, and neutron is slightly heavier than proton, but differ in charge. The proton has positive charge equal to 1 elementary charge plus 1, and the neutron is a neutral particle with no charge at all. The charge of the nucleus is the charge of the nucleus is equal to the sum of the charges of protons in it. An atom has many electrons revolve around the nucleus as there are protons in the nucleus. So, as a whole, the atom is neutral. So, an electron is a light particle, and its mass is 1836 times less than the mass of proton or neutron. So the mass of an atom is almost entirely determined by the mass of its nucleus. And the electron is a negatively charged particle with an elementary charge -1. So the atom is a whole, as a whole, is electrically neutral, let us say. So the described model of an atom is called planetary. And the slide shows the structure of the helium atom. Next please. So all substances contain atoms, which in turn consist of the basic particles, protons, neutrons, and electrons. To display the properties of the atomic particles, a special sign X is indexes A, Z, and N is used, where X is a particle symbol, A is the number of nucleons, the sum of neutrons and protons in the nucleus. Z is the charge of the particle. So protons and neutrons have a complex internal structure that can be described in terms of elementary particles and nuclear forces. Within the nucleus, protons and neutrons can turn into one another while emitting neutrinos or antineutrinos, elementary particles with so-called zero charge and mass close to zero. Of course, if you are people from astrophysics, we will say that mass of neutrino and antineutrino is not zero, but that is another story. It is not the subject of this course. Next, please. So the chemical properties of atoms and their ability to combine with each other, forming molecules, depend on the number of electrons in the atom, on how they are connected with the nucleus, how they are distributed over the shells. It is customary to denote the number of protons in the nucleus or the number of electrons in the shell of an atom by the letter Z. And the number of electrons, and the number of neutrons by the letter M. The total number of nucleons in the nucleus Z plus N is called the mass number and is denoted by the letter A. The slide shows the location of A, Z, and N related to the chemical symbol. A synonym of the atom is the term nuclide. The general name of atoms with a certain number of protons and neutrons. The nuclear charge is the main characteristic of the chemical properties of an atom, indicating its belonging to a particular element. Since the atom is electrically neutral, the positive charge of a nucleus must be equal to the negative charge of electrons in the shell. Therefore, the number of electrons in the atom is equal to the number of protons in the nucleus. Nuclides with the same atomic number Z are called isotopes. As a rule, the chemical properties of isotopes are the same. The current notation for nuclides is X with A, Z, and N, where X is a symbol for the element. For example, an atom containing 55 protons, 82 neutrons, and therefore 137 total amount of nucleons, and 55 orbital electrons in the element is the element cesium, and is designed as cesium. And sometimes we have possibility just to omit some of these additional indexes, because all isotopes of cesium will have, elements cesium, and all isotopes will have the same CS sign for the cesium. That means all of them have 55 protons. That means we can omit 55. Amount of neutrons can be derived we have mass number and amount of protons. So we can omit amount N and Z from this notation. And the possible ways of representation of cesium will be cesium with 137 index on top, or cesium-137. It's normal in practice. Next please. Atom is a neutral structure of a positively charged nucleus and negatively charged electrons in the electron shell. This structure is stable and does not interact with other atoms, such as when identical atoms are dispersed in a vacuum. If the electron of an atom is given excess energy, then this can break the forces that bind the electron and the nucleus. Such an electron becomes free and leaves the electron shell. The rest of the atom becomes positively charged. This structure of the nucleus with an incomplete electron shell is called a positive ion. The physical process that gives rise to positive ion is called ionization. If an atom is placed in a medium that interacts intensively with it, for example, water, the atom will occur wider, actually, another stable structure. It can lose a few electrons from the shell and become a positive ion, or it can capture a few electrons and become a negative ion. These possibilities depend on the interacting medium and the structure of the electron shell, which determines the chemical properties of the atom. Positive and negative ions can interact and form more or less stable compounds, substance molecules. The chemical properties of a molecule are different from the properties of the atom, whose ions are part of the nucleus. Next, please. Number of protons in the nucleus determines what chemical element an atom is. An atom which is a single proton is a hydrogen atom. These are over 100. There are over 100 known elements, sorry, and all of them are represented in the periodic table of elements. The table reflects the periodic law formulated by Mendeleev in 1869. The properties of chemical elements are in periodical dependence on the charge of their atomic number. This law establishes the periodicity of changes in the structure of electron shells of atoms, which determines the periodicity of the chemical properties of elements. In the periodic system of elements, each chemical element has a number that matches the number of protons, Z, in the nucleus, and the atomic mass is indicated taking into account the isotopic percentage composition of the element. The vertical columns of the periodical table denoted by Roman numbers. But you probably saw this in textbooks. Determines the vertical columns of the periodical table contain elements with a similar structure of other outer electron shells, which determines the similarity of their chemical properties. For example, all elements of group 8 have completely built shells. Therefore, they have they behave like chemically inert substances. Or group 7 elements are non-metals that form negative ions with a charge of -1 and are highly reactive. Group 1 elements are alkali metals that form positive ions with a charge equal to +1 and have a very high chemical reactivity. All nuclei can be divided into stable, which can exist for trillions of years or more without any changes, and unstable, or just unstable, which over time turns into other nuclei with the emission of a particle. Currently, 256 stable isotopes of all chemical elements and more than 2,000 unstable isotopes are known, mostly artificially obtained in the time that has passed since the discovery of the phenomenon of radioactivity by Henri Becquerel in 1896. An isotope with a given Z and N is called a nuclide. And if the isotope is unstable, then a radionuclide. For example, lead has 4 stable nuclides and 20 radionuclides. Some elements have only 1 stable isotope each. For example, beryllium, sodium, aluminum, magnesium, iodine, and some others. And elements such as cadmium, tellurium, 8. Tin has 10 isotopes. If an atom is unstable, then over time, the state of its nucleus changes spontaneously, and the nucleus breaks up into fragments consisting of subatomic particles. This process is called nuclear transformation or nuclear decay when it occurs in the nucleus of an atom. For example, hydrogen 1 and hydrogen 2 are stable atoms. On the other hand, hydrogen 3 or tritium is an unstable atom or radioactive. One of its 2 neutrons is converted into an electron, a proton, and antineutrino. Now we have 2 protons and 1 neutron in the nucleus. Hence, a new element has been created. This element is called helium-3. During this process, an electron is expelled from its tritium atom, and a helium-3 nucleus, a positive helium-3 ion, actually, appears, which seeks to capture an electron from the environment to become a neutral atom. The phenomenon of spontaneous nuclear transformation is called radioactivity. Unstable isotopes are referred to as radioisotopes or radionuclides. Isotopes are nuclides that have the same mass number and are therefore the same element, but differ from each other in the number of neutrons. All isotopes of an element have the same distribution of electrons in the orbits. Therefore, their chemical properties are the same and are determined by the position of their position in the periodical table. Sorry. The exceptions are the lightest isotopes, which have the smallest size, hydrogen isotopes. The first isotope of hydrogen is designated H with index 1 on top. The second is usually called deuterium and is denoted D, or H with index 2 on top. And the third isotope is usually called tritium and is denoted as T, or H with index 3. The difference in their atomic masses is so great that it also affects their chemical properties. There are 256 probably. Yeah. There are 256 stable nuclides and over 2,000 unstable, as mentioned before. Most elements have several stable isotopes. several unstable radioactive isotopes. For example, natural lead is a mixture of them and consists of 1.48% of lead 204, 23.6% of lead 206, 22.6%. Lead to 207 and 52.3% of lead 208. Cesium has one stable isotope that can be found in nature, cesium 133, and about 20 radioactive isotopes. All known nuclides are placed in one table. In each cell of each one nuclide is placed in such a way that the number of corresponding columns is equal to the neutron number n, and the row number is equal to the proton number z. We will get the table of nuclides. The initial section of such a table is presented on this slide. The vertical axis is the charge number z. The horizontal one is the number of neutrons n. A row in the table represents isotopes of the same element. Stable isotopes are in blue cells, unstable in pink and yellow. The slide represents the beginning of the table of nuclides with its isotopes of hydrogen, helium, lithium, beryllium, boron, and probably carbon. Physical properties of isotopes, their stability, depend on the number of protons and neutrons in the nucleus. The number of neutrons in the nuclei, stable isotopes of certain elements, is related by an approximate ratio derived from Weizsäcker formula. Number of protons and neutrons the blue line can be described by empirical formula. Let's show. So in unstable nuclei, the neutrons are in an excited state and must release energy in order to reach the state of a stable nucleus. This process is called radioactive transformation. As mentioned earlier, radioactivity is the end result of an imbalance between neutrons and protons in an atomic nucleus. What is important to remember here is that radioactivity is a process, not a state. The fact that a substance is radioactive means that it emits radiation as a result of the nuclear transformation of some of the radionuclides it contains. The amount of radioactivity depends on the intensity of the decay process. During the transformation of an unstable nucleus into a more stable one, energy is released in the form of radiation of charged particles, like beta or alpha particles, in rare cases, protons, and electromagnetic radiation quantum, photons. Photons arising from nuclear transformation are also called gamma quantum. This radiation, when interacting with matter, are capable of converting atoms and molecules into ions. Are ionizing. The radioactive atom always emits ionizing radiation. Radioactivity surrounds man everywhere. Any natural substance around us contains natural radionuclides such as potassium-40, uranium-8, thorium-242, etc. Artificial radioactivity can be obtained as a result of nuclear reactions. First, adding a neutron to the nucleus or removing a proton from the nucleus. Second type, removing a neutron from the nucleus or adding a proton to the nucleus. In practice, reactions of type 1 can be produced by irradiating a substance with neutrons in a nuclear reactor, resulting in neutron-rich radionuclides. Reactions of type 2, when a substance is irradiated with protons at an accelerator. Neutron-deficient radionuclides are obtained as a result. During radioactive decay, both the charge number Z and the mass number A of the nucleus change. The main types of radioactive decays are beta decay. Usually we distinguish three types of beta decay: beta minus decay, beta plus decay, and electron capture. Besides this, alpha decay, isomeric transition, and spontaneous fission. First, starting from beta minus decay. It occurs when the nucleus has too many neutrons. It is enriched with neutrons and is called neutron rich. The transformation of an extra neutron into a proton can lead to a more stable state of the nucleus. This phenomenon is accompanied by the emission of an electron, called beta minus particle, and an antineutrino. It's particle with a tilde. An antineutrino has no mass or charge. With charges, everybody agree, but mass is already measured. It's like electron volts. But if you compare with the mass of beta particle, resting mass of electron, it is 511 kiloelectron volts. So we can omit this mass of antineutrino. Beta minus an antineutrino has no mass or charge, so the mass number of nuclides during beta minus decay remains unchanged, while the charge number of the daughter nucleus increased by 1. This event can also be represented as this example: decay of neutron gives us proton plus electron, beta minus particle, then antineutrino and kinetic energy. And another example, cesium-137 has such an opportunity, beta minus decay to barium-137 metastable. Plus, of course, electron and antineutrino, and of course, some energy. A daughter nucleus is a different element from the parent element because it has a charge number increased by 1. So this different element power. Almost all of the total energy released during beta decay is distributed between electron and antineutrino. So beta particles are emitted with a continuous energy spectrum, extending from 0 to a maximum value dependent on the radionuclides. Their minimum energy is 0 and maximum Q beta. Usually in the reaction, you know this. Some beta emitting radionuclides can leave daughter nuclei in an excited energy state, like in an example with barium. And their stable state is achieved by emitting one or more gamma rays further. The second type is beta plus decay. Occurs when the nucleus has so many few neutrons. You can say many protons. Usually we say too few neutrons. It is neutron deficient. The transformation of a proton into a missing neutron can lead to a more stable state of the nucleus. This phenomenon is accompanied by the emission of a positron. Positron is a beta plus particle, which is the same like electron, but antiparticle will, according to the electron. And neutrino without addition of anti. Antineutrino has again no charge and mass, so in case neutrino, sorry. So the mass number of nuclides during beta plus decay remains unchanged, while the charge number of the daughter nucleus decreased by 1. This phenomenon can be represented by this example: decay of proton to neutron, positron, and neutrino, and of course kinetic energy. And another example is fluoride 18. Also have the possibility to take beta plus decay. We obtain oxygen 18. We will see positron and neutrino. And you will see this reaction if you will go to medical center, and you will get such a procedure like positron emission tomography. Usually it is injected with the blood to see distribution in the body. Daughter nucleus of beta plus decay is a different element again, like in beta minus decay. We compare with parent element, so which has a charge number reduced by 1. The total energy released during decay is almost all distributed between the positron and the neutrino. So the beta particles are emitted with a continuous energy spectrum, like in the previous case, that extends from 0 to a maximum value depending on the radionuclide. Their minimum energy is 0, the maximum Q beta. Positron, an elementary particle similar to the electron, but having a positive charge. The positron is the antiparticle for the electron. When breaking in a medium, the positron loses its energy and in a very short period of time interacts with the sum of 3 electrons. Such an interaction leads to the annihilation of these particles, while their mass is converted into the energy of electromagnetic radiation. And 2 gamma quanta are formed with an energy of 0.511 MeV each. So the write the reaction, but like electron plus positron gives us kinetic energy only. The need for the annihilation of an electron and a positron to produce not 1 but 2 gamma quanta follows from the momentum conservation law. The total momentum of the stopped positron and electron before the transformation process is 0, but it cannot be 0 when only 1 gamma quantum is formed due to the annihilation. Here is electron capture, the third type of beta decay. Electron capture occurs when the nucleus has too few neutrons. It is depleted in neutrons, neutron deficient. The capture of a free electron by a nucleus leads to the transformation of a proton into the missing neutron, and the transition of the nucleus to a more stable state. This phenomenon is accompanied by the emission of neutrinos. A neutrino has no mass or charge, so the mass number of nuclides during the beta plus decay remain unchanged, while the charge number of the daughter nucleus decreased by 1. Decreased like in the previous case of beta plus decay. This phenomenon can be represented in this case: proton plus electron gives us neutron and neutrino. Or Another example, iodine 125 plus electron gives us tellurium 125 plus neutrino and energy. Electron capture is a nuclear transformation that competes with beta plus decay. Typically, neutron deficient nuclei can experience both types of nuclear transformation. So next one. Now we have heavy artillery. The alpha decay. Alpha decay occurs only in very heavy elements with a charge bigger than 83, such as uranium, thorium, rhodium, etc. The nuclei of these atoms are very rich in neutrons. These atoms have many more neutrons in their nuclei than protons, which makes it possible to emit alpha particles. After the nucleus ejects an alpha particle, a new parent nucleus is formed with two fewer neutrons and two less protons. Therefore, when uranium-238, which has number of protons equal to 2, in case to emit an alpha particle, thorium-234 is formed. Decay can be represented as a reaction. Here is example is plutonium, actually. Another example. Plutonium has 239 nucleons, and after alpha decay, we can see uranium-235 plus alpha particle and energy. An isomeric transition occurs when the nucleus of an isotope can have an increased energy for a long time and be in a metastable state, and then spontaneously emits an excess of energy in the form of a gamma quantum and return to the ground state. The charge and mass numbers of the isotope do not change during the isomeric transition. So the isomeric transition can be represented as following example: barium-137 metastable can come to the more efficient position of barium-137 without extra M and released energy. Some atomic nuclei have several isomeric states with different lifetimes, that means half-lives. Spontaneous fission is a nuclear transformation in which a heavy unstable nucleus randomly fissions or splits into two or more light nuclei, usually releasing 2 or 3 neutrons and a significant amount of energy in the form of gamma radiation, beta radiation, neutrino, and kinetic energy of fission fragments, as well as neutrinos and photons. Spontaneous fission is a nuclear transformation that competes with alpha decay. For most alpha-emitting radionuclides, the probability of spontaneous fission is negligible. The most important radionuclide that has a significant spontaneous fission probability is californium-252. Spontaneous fission probability of californium-252 per alpha decay is about 3.1%. A substance that contains californium-252 is a source of neutrons with a continuous energy spectrum. As a rule, fission fragments are rich in neutrons and undergo beta-minus decay. In addition, fission fragments are born in a highly excited state, and the removal of their excitation is accompanied by prompt gamma radiation. So here is the general scheme. During radioactive decay, both the charge number Z and the mass number A of the nucleus change. If we depict the transformations of nuclei during various types of decay in the coordinates Zn of the table of nuclides, we will obtain a scheme of nuclear transformations represented on one slide. Nuclear transformation results in the movement of nucleus from one cell far from region of stability towards a cell located closer to this region. For nuclides rich in neutrons, the most probable transformation is beta minus decay, when the converted nucleus moves one step up and one step to the left in the table. For neutron poor, neutron deficient nuclides, the most probable transformation is beta plus decay or electron capture, when the converted nucleus moves one step down and one step to the right in the table. For nuclides heavier than bismuth, alpha decay becomes possible when the converted nucleus moves 2 steps down and 2 steps to the left in the table. Most of the daughter nuclei resulting from alpha decay are rich in neutrons and have a high probability of further beta minus decay. Radioactivity. Second. Radioactivity is the end result of an imbalance between neutrons and protons in the nucleus of an atom. All stable nuclides are located in the table of nuclides along a relatively narrow band called the stability track, as shown on the slide. In the shells of light nuclides in stable nuclei, the number of protons and the number of neutrons is almost the same, approximately equal, Z and N. Starting with A greater than 40, usually the number of neutrons bigger than the number of protons. It must be emphasized that all nuclei with charge number greater than 83 after bismuth are unstable. And in addition, nuclei with charge number 43 neptune and 61 promethium also do not have a single stable isotope. Another thing, at mass number 209, bismuth 209 actually, the stability track ends, which is indicated on the slide at the area with long-lived nuclides. Actually, after this, we can see the island of stability, but it is also another story. Physical properties of isotopes is their stability. It depends on the number of protons and neutrons in the nucleus. So, a radioactive source cannot exist forever. The number of radioactive nuclei in it is constantly decreasing due to their spontaneous transformation. The word spontaneous means that the decay of each nucleus is absolutely unpredictable. It can happen in a moment and in millions of years. A radionuclide that undergoes a spontaneous transformation is called a parent. And a new nuclide resulting from such a transformation is called a daughter. If the daughter radionuclide is not stable, then as a result of its transformation, the next generation nuclide, granddaughter, etc., appears. A chain of radionuclides connected by kindly is called radioactive family. As a result of radioactive decay, the number of nuclei of the parent radionuclide constantly decreases, while the number of nuclei of the daughter radionuclide, if it is stable, increases. This transformation is subject to the law of conservation of the number of nuclei, which can be formulated as follows. The total number of nuclei members of the radioactive family is a constant value. The period of time during which 50% of the nuclei of the parent radionuclide decay It's called the half-life. If we start observing a radioactive source at time t0, then at the time t0 plus half-life, half of the initial number of nuclei of the parent radionuclide will remain in the source. At the point of time t0 plus 2 half-lives, we will have only 25% of the nuclei. So the activity of any radionuclide in the source becomes less than 1% of the original after 7 half-lives. Chains of radioactive transformations can be elementary, simple, and complex. Elementary chains contains only the parent radionuclide and one stable child. In simple chain, the decay of the parent radionuclide leads to the formation of only one daughter radionuclide, and so on. In this case, the decay of each member of such a radioactive family always leads to the appearance of one daughter nuclide. Complex decay chains are branching structures. They occur when as a result of the decay of individual radionuclides in a chain. Two or more different radionuclides can be formed. The slide shows examples of such decay chains. The parent radionuclides and their descendants from a radioactive chain or radioactive family. The chain of decay stretches the chain of radioactive decays stretches until a stable nuclide arises as a result of nuclear transformation. The sum of nuclei in a radioactive chain obeys a special conservation law. The sum of nuclei in any chain is a constant. During the decay of a heavy element that are far from the region of stability, decay chains or radioactive families arise with a large number of radionuclides. For example, a complex chain of decays generated by the nuclear transformation of radioactive natural isotope uranium-238 ends with the formation of a stable Rad-206 and contain 18 radioactive descendants. In the nature, there are 3 radioactive families, starting with radionuclides uranium-238, uranium-235, and thorium-232. These families are usually called uranium and thorium respectively. The most significant radionuclides in nature are the radioisotopes of radon. Of course, this sentence is related to physicists, not for all physicists, because radon plays the tremendous role in our course. These radioactive gases, actually, yes. These families are usually called uranium and thorium. The most significant radionuclides in nature for us, radioisotopes of radon-222 and taron. It's radon-220. That have the same sign, but different source. So the first one comes from the uranium-238, and the second one from chain of thorium. These radioactive gases came from rocks containing uranium-238 and thorium-232, and responsible for from 50 up to 80% of background radiation exposure to humans during the year. The slide shows the components of the uranium family. A nucleus of uranium-238 is unstable but long-lived. It occupies a position in the table of nuclides far from the line of stability. The nucleus of uranium-238 must go through 14 transformations to get to the line of stability in the form of nucleus of slave 206. Along this way, the parent nucleus loses 32 nucleons in 8 alpha decays. The other decays are beta minus, beta plus, probably. Most of the daughter nuclides arising from alpha decay must be rich in neutrons and undergo beta minus decay. Therefore, the decay chain of uranium-8 is a set of large number of alpha and beta minus decays. Each of them is a step forward to the region of stable nuclei. Red lines represent alpha decay, and blue lines represent beta minus decay of radionuclides in the uranium family. The section of the slide starts from starting from radon 222 and coming to lead 210. The center, most important for the relativists. Radionuclides from this side are present in natural aerosols, which forms the bulk of natural human internal exposure. When the nucleus of an atom decays, it gives of some of the excess energy in the form of gamma rays and or fast particles. If an atom decays with the emission of an alpha or beta particle or undergoes spontaneous fission, then it becomes a new element. Therefore, radioactive substances emit energy in the form of alpha particles, beta particles, and gamma quanta. When these radiations interact with matter, they can, under certain circumstances, initiate nuclear reactions, resulting in the emission of protons and neutrons. Gamma rays are of the same nature as visible light. Like all forms of electromagnetic radiation, the gamma rays has no mass or charge. Energy is one of the most important characteristics of neutron radiation. The energy, nuclear radiation, the energy of all these radiations is expressed in units called electron volts. 1 electron volt is equal to 1.6 10 to minus 19 joules. And usually we use electron volts, kilo electron volts, and mega electron volts, the derivatives. Radiations typically have Radiation typically have an initial energy measured in thousands of electron volts. It will be kilo electron volts, and million. It will be mega electron volts. The emission of ionizing radiation accompanies the transformation of nuclei. In general, all radiation can be divided into two main categories: indirectly ionizing and directly ionizing, depending on the ability to ionize the substance. Ionizing radiation is called the interaction of which this matter is to the ionization of atoms and molecules. It is to the appearance of ions of different signs in the irradiated substance. Probably one word is skipped here. The ionization of atoms and molecules is the main process of transferring radiation energy to matter. This complex process can be divided into two parts: distribution of primary radiation from the source to the point of interest was in the substance, and transfer the radiation energy to matter of this point. As a rule, these processes have significantly different spatial scales. The propagation of primary radiation is carried out at considerable distances from the source. For example, neutrons and gamma quanta propagate to meters even in a dense medium, and in air to hundreds of meters. The transfer of radiation energy is carried out within the limits of the ranges of charged particles in the substance. The maximum path length of charged particle particles in biological tissue, as a rule, do not exceed tens of millimeters. During the transformation of nuclei, the decay products, daughter nuclei, particles, and photons have different energy distributions. This distribution depends on the type of decay. The energy distribution of R-type particles is the energy distribution of these particles. So it's actually represented by formula. N is equal to Dn capital to dE, but not necessary for our slide. So the slide represents the alpha decay spectrum. The alpha particles have a mass and charge equal to the mass and charge of helium nucleus, 2 protons and 2 neutrons, and are emitted during the decay of heavy nuclei. An example below is X, the nucleus X, represent having the alpha particle or alpha decay comes to another nucleus and plus alpha particle. During alpha decay, energy, momentum are distributed between 2 particles. You know them completely. Daughter nucleus and helium-4 nucleus. And the remaining daughter nucleus can be both in the ground state and in the excited state. Excited states are characterized by certain values of excitation energy. Therefore, for each state, the alpha spectrum will be represented by a discrete set of energy values. It can be depicted as vertical lines, the length of which is proportional to the probability of decay into one or another state of the daughter nucleus. The energy of alpha radiation is limited to the range from 2 and up to the 12 MeV. Beta decay in a nuclear transformation having 3 particles: electron, a nucleus, and an antineutrino in the case of beta minus decay. And as a decay product of the parent radionuclide. In this case, the decay energy Q beta distributed between a positron and neutrino, if it is beta plus decay. As a result of this distribution, charged particles produced by beta decay have a continuous energy spectrum. This type of nuclear radiation is called beta radiation, and its energy spectrum is called beta spectrum. The sign minus or plus are used to emphasize the type of decay. Quantitative characteristics for the beta spectrum will be maximum energy, Dmax, and average energy. Average energy of beta particles is equal to maximum divided by the 1/3 of the maximum. The minimum energy of beta particles is 0. The mechanism of beta decay limits the energy of beta radiation to about 4 MeV, maximum energy of beta spectrum. Photons are indirectly ionizing electromagnetic radiation, which are classified as follows. X-rays are photons emitted during the transition of orbital electrons between energy levels. They have a discrete energy spectrum. Bremsstrahlung occurs when an electron decelerates in the Coulomb field of the nucleus. Gamma rays are emitted during the transition between energy levels in the nucleus. It can also be emitted during the other decay modes. Gamma rays have a discrete energy spectrum. Annihilation quanta are photons with an energy equal to the rest mass of an electron or positron, which is equal to 511 kiloelectron volts. Occur during the annihilation of an electron and a positron. There are always 2 annihilation quanta. The de-excitation mechanism by emitting photons limits the maximum energy of gamma rays to about 7 MeV. The number of photons emitted as a result of the nucleus transformation, as a rule, is not equal to 1. Magic thing. This little table of ionizing radiation represents the relationship between the type of radioactive decay and the type of ionizing radiation, and also with the energy spectrum. Cells containing C represents radiation with a continuous spectrum of energies. Cells containing D represent radiation with a discrete energy spectrum. And cells containing minus indicate that the radiation in question is not possible or has a very low probability for this type of nuclear transformation. Cells containing D or minus or dash show that in some individual cases the radionuclides are pure beta minus emitters or alpha emitters that do not emit photons during transformations. Examples of pure beta minus emitters are tritium, carbon-14, phosphorus 32, and cesium-135. Examples of pure gamma emitters is barium-137 metastable or technetium-99 metastable. Both of them are applicable in the nuclear medicine, for example. And examples of pure alpha emitters, gadolinium-148 and samarium-146. During the decay of radionuclide, several possible variants of the final state of the daughter nucleus may arise. It is important to note that most alpha and beta emitters also emit photons during decay. However, there is no one-to-one correspondence between the number of nuclear transformations and in the radioactive substance and the number of photons or particles emitted per unit time in this substance. Only in some special cases does such a one-to-one correspondence exists. For example, in the case of pure beta minus decay of tritium or strontium-90. Case of nuclear transformation of copper-64, an example of the opposite situation. The slide shows the decay scheme of copper-64. This radionuclide occupies a position in the table of nuclides close to the stability region. In 37.2% of the case, it can become stable zinc-64 through beta minus decay. In 44.9% of the case, it can go into stable nickel-64 through electron capture. And in another 17.9% of the case, it can also go into a stable nickel-64 to beta plus decay. Therefore, if the substance contains 1 becquerel of copper-64, then only 0.55 beta particles appear in it in 1 second on average. If we just add up 0.37 and 0.18. So this general rule of radioactive decay can be formulated as follows. The average number of particles or photons emitted by a radioactive substance in a given period of time is not equal to the average number of nuclei that have undergone transformations in the substance in the same period of time. This is very important for understanding the results of radionuclide contamination monitoring. If, for example, it is necessary to determine the total specific activity of a sample and the result of the measurements, the number of particles of quanta that occur in the unit mass of substance per unit time, then this problem can be solved only if the radionuclide composition of the contamination is known. Radiation imparts energy to matter through ionization and excitation of atoms and nucleus. Coulomb forces play a major role in these processes. Moving charged particles has an electric field surrounding it that interacts with the atomic structure of the medium it passes through. This interaction slows down the particles and accelerates the electrons of the atoms in the medium. The accelerated electrons can give enough energy to escape from the parent atom. This process, by which radiation strips orbiting electrons, is called ionization. These charged particles are the main radiation that ionized and excited atoms and molecules, and directly transfers the energy to matter. Uncharged particles and photons do not have an electric field, so they can only lose energy and cause ionization through processes such as absorption or scattering. Neutron and photon radiation transfer the energy to matter in a two-stage process. At the first step, this radiation interacts with the nucleus, with neutrons, or an electron from the shell of an atom. So, the gamma radiation interacts with electrons, and neutrons interacts with nucleus, of course. The secondary charged particles arising as a result of these processes are the products of energy dissipation of primary uncharged particles in metal. At the second stage, secondary charged particles transfer radiation energy to matter. Therefore, the interaction with matter is divided into two main types. Charged particles directly ionize the medium they pass through, while uncharged particles and photons can only cause ionization indirectly or through secondary charged particles. The interaction of neutrons with matter is so weak and is not taken into account. Direct ionization of atoms and molecules by charged particles is the main process of transformation or transferring radiation energy to matter. The ionization of an atom is a result of the transfer of radiation energy to the electrons, to the electronic structure of an atom. Ionization occurs only when enough energy is transferred to remove an electron from the shell. Therefore, this energy must be greater than the binding energy of individual orbital electrons. The energy required to produce one ion pair in a substance ranges from 5 to 40 electron volts. For liquid water, for example, it is about 19 electron volts and doesn't depend on the type of charged particle. Therefore, when any charged particle transfers 100 kiloelectron volts of its energy to water, this results in the production of about 5,000 ion pairs. The degree or intensity of ionization or specific ionization is defined as the number of ion pairs created per centimeter of path of a given substance and is proportional to the mass of the particle and the square of its charge. So the mass of an alpha particle is about 7,300 times the mass of electron, and the charge is 2 times greater. So an alpha particle can produce much more ionizations per unit path length than a beta particle with the same energy. This phenomenon occurs when the larger the mass of an alpha particle, the slower it moves at a given energy, and therefore interacts with electrons from the shell of an atom for a long time, sufficient to knock more electrons out of the atomic shell. Like alpha particles, heavy charged particles like protons, neutrons, recoil nuclei, when interacting with matter, participate in three main processes: excitation, ionization, and absorption. Excitation and ionization. Alpha particles, like other heavy charged particles, interact intensively with the electrons of an atom due to their strong positive charge. They act with Coulomb forces that affects electrons at a great distance on the scale of atoms, pulling electrons out of the orbits. Since the particles interact intensively with the electrons of the atom, they have a short path length and move in a straight line. Straight shows straight arrows on this red arrows picture. Such radiation is called strongly ionizing radiation. So there's an additional empirical rule. Alpha particle range in the air is equal to 0.3 the energy in power in the three house, where E is represented in megaelectron volts. Absorption, another option here for alpha particles or heavy ions. In an absorption reaction, a proton or alpha particle is actually absorbed by the nucleus of an atom, and the atomic nucleus becomes excited. Atoms under such conditions are unstable, and the main mechanism by which they return to a stable state is the emission of nuclear radiation. An important example of an absorption reaction is the capture of alpha particles by the nuclei of light elements like beryllium, boron, carbon, nitrogen, oxygen, and fluoride. The result of these reactions is the emission of neutrons. So if alpha particles interact with beryllium, for example, we can obtain carbon-12 and neutron, and of course release some energy. This reaction is widely used to produce radionuclide neutron sources. An alpha particle, when stopped in a substance, captures a couple of free electrons and becomes helium-4 atom. The accumulation of helium is one of the factors limiting the service life of sealed encapsulated radionuclide sources. Same slide for better. Passing through matter, electrons experience elastic and inelastic scattering or interactions with the atoms of the medium. The elastic ones includes elastic scattering. The inelastic ones includes the excitation and ionization of the atoms of the medium, as well as the appearance of Bremsstrahlung. German word. Interactions of the first type determine the deviation of the electron from the initial direction of motion in matter. The second one, the transfer of energy to matter. Excitation and ionization. Ionization by electrons differs from ionization by heavy charged particles. Beta particles with their lower mass, lighter velocity, higher velocity, and unit charge transfer the energy in rarer interactions than alpha particles or protons of comparable energy. Since the mass of the interacting beta particle is equal to the mass of the orbiting electron, a large angle deflection can occur with each interaction, resulting in many kinds of the trajectory or scattering. So it changes direction very rapidly. So the other empirical rule for the calculation of range of beta particles in the medium the range is equal to energy divided by 2. If energy is represented in megaelectron volts. And another story, Bremsstrahlung. As an electron approaches the nucleus of an atom, its speed first increases, and then decreases as it moves through the electric field of the atom. First approaching the nucleus and then moving out of it. Acceleration and then rapid deceleration of the beta particle leads to the emergence of electromagnetic Bremsstrahlung. The Bremsstrahlung energy has a continuous spectrum from 0 to the initial kinetic energy of the incident electron. Bremsstrahlung carries the energy over a long distance and transforms beta source into a source of penetrating radiation, gamma radiation. Another rule for this case. For beta particles, the average energy of Bremsstrahlung does not depend on the properties of the protective medium and is about 16% of the maximum energy of beta spectrum. And stopped in a substance, electrons are just captured by ions. For positron, all the same like for electrons, but we have little addition. We have to mention here the annihilation. It is the only interaction that distinguishes between positrons and electrons. During annihilation, the mass of electrons and the positron is converted into energy in the form of two gamma quanta with energy 511 kiloelectron volts. The immediate from the annihilation point at the angle of 180 degrees to each other. The need for the annihilation we already discussed here instead of one. Neutrons and photons. Indirectly ionizing radiation consists of neutrons, neutral particles like neutrons and photons. The transfer of energy from indirectly ionizing radiation to matter occurs in two stages. When interacting with the medium, directly ionizing radiation is formed. In this process, the main part of the energy of neutrons and photons is lost. Directly ionizing radiation formed at the first stage transfer energy to matter. Primarily, photons and neutrons passes through matter, lose energy in rare collisions with electrons of the atomic shell and atomic nuclei. The probability of such a collision is low, so neutrons and photons can penetrate matter for a long distance without significant loss of their energy. This radiation are called strongly penetrating radiation. The products of these collisions are secondary charged particles, high energy electrons and positrons in case of photon penetration, and equal nuclei and unstable nuclei in the case of neutrons. The products of these processes are secondary electrons or ions with high energy, which transfer the energy of primary photons and neutrons to matter in a certain area surrounding the point of interaction of the primary particles or photons. The energy of the secondary particles is dissipated in matter as a result of ionizing and excitation of atoms. The interaction of gamma quantum with matter is a rare event which causes the propagation of gamma radiation over considerable distances. At the point of each such interaction, secondary fast charged particles, an electron or a pair of electron and positron are born, to which the primary radiation transfer radiation transfers all the energy or part of it. Secondary charged particles propagate in a local area around the point of primary interaction, transferring their energy to matter. In fact, in acts of ionizing and excitation, all ionization associated with the transfer of energy of gamma quanta to matter occurs under the action of these secondary particles. Photons themselves act as indirect ionizing radiation. So we can mention here three main effects of interaction of gamma quanta with the matter: Compton effects, photoelectric effects, and the effect of electron-positron pair production. Due to the fact that neutrons do not have charge, they lose their energy practically only when interacting with the nuclei of atoms of the medium and have a high penetrating power. The interaction of neutrons with matter is a random process that includes three effects: elastic scattering, inelastic scattering, and absorption. The first one, the neutron collides with nucleus and bounces off it. In this case, some part of the kinetic energy of the neutron is converted into the kinetic energy of the atomic nucleus, leading to the slowing down of the neutrons. If the mass of the nucleus is comparable to the mass of the neutron, then this process becomes most noticeable. For example, in the scattering of neutrons by hydrogen nuclei, materials containing hydrogen slow down neutrons most effectively. In one collision, it can lose up to 50% of its energy. Inelastic scattering. In an inelastic scattering reaction, a neutron nucleus collision occurs in the same way like in elastic scattering. However, in this reaction, in addition to the kinetic energy, the internal energy of the nucleus also increased. When the nucleus returns to its original energy level, it usually emits gamma rays. And last but not least, the process is absorption. In absorption reactions, the neutron is actually captured by the nucleus, and the nucleus of the atom is in an excited state. Nuclei return to their ground state by emitting nuclear radiation, usually in the form of accompanied by photons. If the nucleus emits only photons to reach the ground state, the process is usually called the radioactive capture. Some of the stable isotopes present in the human body are very efficient in capturing neutrons, like hydrogen, sodium 23, sulfur 34, and potassium 41. The radiation of radionuclides in these reactions does not make a significant contribution to the irradiation of biological tissue, but the gamma radiation, can be used to estimate the dose in the event of accidental exposure to neutrons. Okay. So different types of radiation penetrate matter differently. Alpha particles intensively loses its energy to ionization and excitation. Therefore, they have the least penetrating power of the four types of ionizing radiation. They can be stopped by the list of the sheet of thin paper or clothing. Substances that emit alpha particles can only affect a person if they are ingested. Alpha particles can only penetrate just 0.07 millimeters thick protective skin layer. if the energy exceeds 7.5 mega electron volts. Therefore, alpha radiation usually possesses an intrinsic hazard. Beta particles or electrons are less ionizing than alpha particles. Electrons can only penetrate the 0.07 millimeters thick protective skin layer. If the energy exceeds 70 kiloelectron volts. Beta radiation usually possesses an internal and external hazard to organs and tissues located close to the surface of the body. Photons are one of the most penetrating types of radiation. They lose energy in interaction with the electron of matter. The more electrons per unit volume of a substance, the more likely such an energy transfer is. So the range of photons in many matters in air and centimeters. The range of photons in many meters in the air and centimeters in dense material is high charge number. Thus, photons represent an internal and external danger for a person. Neutrons are the second most penetrating radiation. Neutrons pass relatively easily through a matter with a large Z charge number, but are quickly absorbed by a hydrogen-containing material. It should be noted that having lost energy in a hydrogen-containing material to thermal energy, a neutron is captured by a hydrogen atom and forming deuterium and emitting gamma quantum with energy of 2.25 mega electron volts. Consequently, the hydrogen-containing shield becomes a source of a gamma radiation, and it is irradiated with neutrons. Thus, neutrons constitute both internal and external danger. A couple words about transition. The interaction of radiation with matter can lead to a radiation conversion. Heavy charged particles. If an alpha particle interacts with a light nucleus, when its energy can be converted into the energy of a neutron, which appears in the alpha N reactions. Some mixture of alpha emitting radionuclides with boron, beryllium, fluoride, or oxygen are intense neutron sources. Thus, alpha radiation usually possesses an internal hazard, but under certain conditions, its energy can be converted into the energy of neutron radiation. It is a penetrating radiation and will possess an external hazard. In case of beta particles, if electrons interact with substances with high charge number Z, their energy can be transformed into the energy of branch current photons. These photons can travel long distances in comparison with beta particles. And neutrons. Interactions of neutrons with matter usually produce recoil nuclei and secondary photons as a result of neutron capture. For sure, the last one. So the radioactivity is a fundamental property of matter. Is the transition of unstable nuclei into more stable ones. This effect produces ionizing radiation. The interaction of ionizing radiation with biological tissue causes the effects of exposure to radiation on human health. The simplest structural unit of any element that can exist while still remaining its chemical and physical characteristics is the atom. The atom consists of central nucleus containing most of its mass and electrons arranged in a shell around the nucleus. The atomic nucleus is made of up to two types of nucleons called neutrons and protons. And the number of protons in the nucleus determines the chemical property of atoms as chemical elements. Some combinations of neutrons and protons in the nucleus are stable. Atoms with such nuclei are called stable atoms. Other combinations of neutrons and protons are unstable and have excess energy. They become stable through the release of energy in the form of radiation. Atoms with such nuclei are called radioactive atoms. Nuclear transformation is an arbitrary process that continues in time. The number of neutrons and protons in the nuclei of radioactive atom determines the physical properties of the nuclei. Half-life of an unstable nucleus, type of nuclear transformation, and the type of energy of radiation emitted as a result of nuclear transformation. Nuclear radiation can be divided into two main groups: charged particles and uncharged neutrons and gamma quantum. Charged particles directly ionize the medium they pass through, while uncharged particles and photons can only cause ionization indirectly through secondary radiation. So that's all for lecture number 1. Any questions? Thank you for your attention. And
En la sala también, si alguien tiene alguna pregunta, puede hacerla y podemos transmitir.
It's time to a little break for 10 minutes, please. Vamos a tomar un reposo de 10 minutos, por favor. Pueden servirse lo que deseen, ahí tenemos una mesita y vamos a volver en 10 minutos.